Hello everyone. In this video, I will cover the first problem of the USACO 2021 January contest Silver Division. So in this problem, we have n cows standing in a line, the ith cow at the ith position. And then we have a sequence of k swaps. And so these swaps are going to swap the cows present at two different locations at any given instance. So for example, we have the first swap swaps the cows at positions A1 and B1. The second swap swaps cows at positions A2 and B2, and so on and so forth. And after the kth one, we cycle again back to the first swap. And so we want to know, after applying these swaps over and over again until the end of time, how many unique positions will each cow end up occupying? So let's take a look at this sample as an example. So in the sample, we have 5 cows. Then we have a swap between, the first swap is between positions 1 and 3. Second swap is between 1 and 2. Then between 2 and 3, and then finally 2 and 4. All right. 1, 3, yes. Okay. All right, nice. So let's go ahead and let's take a look at the first cow, for example. So let's look at the cow that originally starts in the first position. So after the first swap, this cow will swap with the cow in the third position, so it will move over here. Now the second swap doesn't affect it, but the third swap does. So this swap right here, this swap does affect this cow. Specifically, it will move it to here. Then the fourth swap, we'll pull it over here. And now we go back, now we finished all the swaps. We're going to cycle again for the first swap again. So we're going to process the first one, second one, third one. And when we get to the fourth one, that's going to affect this cow because this cow is at one of the positions that the fourth swap affects. So it's going to get pulled back over to positions from 4 to 2. Then we cycle through again, 1. And then when we get to the second swap, that's going to pull the cow back here. So this is a little bit of a complicated path I've drawn here, but basically you can see the first cow ends up occupying positions 1, 2, 3, and 4 at any point, at some point throughout the entire journey. And this cow never occupies position 5. Oh, and to specify, I stop here because if you go through all the swaps again, you'll realize that you basically end up back in the same scenario as the original setup. So having the cow at position 1 and starting back again from the first swap. So how can we approach this problem? Well, a naive solution might be to kind of just take each cow one by one and just simulate the process, right? So something to note here is, how are we going to simulate this process? Because if you naively iterate over each swap as well and each check, then it's going to be it's going to take a long time to possibly finish simulating. We might never finish simulating in a sufficient amount of time. So something we can notice is that, say a cow is standing here at this position, right? And say that currently the time is say it's currently time 0. So this is the beginning of the program before any swaps have taken place. Well, then notice that out of the 2 swaps that are connected to position 1, one of them happens at time 1 and one of them happens at time 2. So obviously the swap with time 1 is going to happen first because it happens at an earlier time than time 2. So we essentially just take if you think about this as a graph, we take the edge with the smallest time, which is going to be 1. So we'll follow this path here. And now we have a cow as at this position, and the time is currently 1. Right? Now, out of the 2 edges coming out of this node, this position, one of them is at time 1, the other is at time 3. The thing is, we can't possibly take time 1 because we can only take, because we just came from there. And also so the next time we would be able to take this time 1 edge, the next time we would be able to take this edge would be after an entire cycle. So at time 5 is really the next time we'll be allowed to take this edge, right? So you see time 3 is less than time 5. So we take this edge. Now when we get to here, we once again have like 2 different options. And right now here we have this reached at time 3. And we have 2 different options here. Well, or actually 3 different options. We have an edge. So we have an edge that is of time 3, an edge of time 2, and an edge of time 4. Now we use the same logic that we just applied. The thing is that we just reached position 2 at time 3. So we're not going to be able to take this edge with a time equal to 3 because basically you can think of as we've already passed, like basically that this swap operation has already occurred. So the next time that we will be able to use the swap operation is time 7, because we have to wait until we cycle through all the swaps again and then go through the list of swaps a second time before we're finally allowed to use the swap that is labeled 3. The same thing applies to this swap right here. We can't use this edge, we can't use this swap because it's already happened. So we need to wait until time 6 before we are allowed to take this swap. Now this one we are able to take at time 4 because 4 occurs at a later time than the current time we're at, which is time 3. So we'll take this edge. And so you can kind of see how the simulation is like sped up, right? Essentially, at a current position, we'll consider all the edges coming out of it, all the swaps that affect this position. Each of these swaps will occur at a certain time. Maybe this is at 2, this is at 5, maybe this is the 8th one, this is the 10th one. And depending on what time it's currently, right, what time we are currently sitting at this node right now, let's say we're sitting at this node at time 3, let me take the next largest, right? So we would take the next largest time at which a swap interacts with this position, which is 5. Notice that instead, if our time was equal to 6, we would take this one. Continuing down this path, if it was time 9, we would take this one. And notice that if it is time 11, right, the next one we would take would actually be this one, because you would have to, because we finished all the, essentially we in this current cycle of K swaps, we've already finished all swaps that interact with this position. So the next time we'll encounter a swap that interacts with this position is at the next cycle. So we start again from 2, which would actually occur at time 13. So I guess take a moment to really think about like how this works. Essentially, we're saying that depending on what time you're currently at a given position, we know which edge or which swap is going to affect this position next. And so this actually gives us, so if we were to do this for every single cow, right? And for each cow, we would just continue like walking, I guess. For each cow, we would initially start at the position they're at and time 0. So essentially we have this like node that's characterized by the position and the time. And we're basically just going to keep, I guess, simulating, keep walking through all the nodes until we get back to this same position at the same time again. And notice that in terms of time, we don't actually keep track of the literal time. We keep track of the time mod k. Mod k. And you can think about why that works, because being at a position at time 1 is the same as being at a position at time 1 plus k, because you have the exact same set of swaps that you were interacting with. And so essentially we just need to keep walking until we get back to this position I comma 0. And so what is the complexity of this solution? Well, how many nodes are there? How many position time pairs are there? Well, the number of positions is n. Number of times is the number of different, could be any of the, from any of the, and actually this should be time mod k plus 1, right? Because 1, 2, 3, dot, 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 up to k, and then 1 again. Yeah. So the number of different positions, the number of position time pairs would be n times k, right? And if we do this for each cow, we get O of n squared times k, which is still way too slow. So how can we speed this solution up? Well, one thing we can notice is that we don't have to do it for every single cow. The reason we don't have to do it for every single cow is because let's actually think about what this graph looks like. This graph is going to be maybe like we have some I, some 0, connects to some other j, that's maybe at time, let's say 5, then maybe you have something like this, time k at index number 8, so on and so forth, right? But it's going to turn out that this is just, it's going to turn out that this is actually just a graph of a bunch of cycles. And to see why this is true, consider a given node. A given node only has one outgoing edge, which is simply the next, like the next swap that it interacts with, and it only has, actually, okay, let me do it this way instead. Okay, so so I argue that's going to be a set of cycles, and if it's not a set of cycles, then well, first off, we know for a fact that a node can only have one outgoing edge, right? A node can only possibly have one outgoing edge. It's just the next time swap that it takes. The next swap that it takes that is like adjacent to this node, to this position. However, is it possible for a node to have more than one incoming edge? Well, it's actually not possible because let's assume that a node does have multiple incoming edges. So say like we have this position here, the first edge is going to come in at time 2, the second edge is going to come in at time 5. We have to remember these edges, these swaps are bidirectional. You can swap in either direction. And this is like, yeah, this is like going outwards. So this is going to be at, oh, actually, yeah, I guess it's an easier explanation. So by definition, you can't possibly have more than one incoming edge because the time is represented by the time component of the time component is what time you arrive at this node. And you can't possibly arrive at this node from two different positions because there's only one edge with this given timestamp. Yeah. So it's actually not possible. So it's just not possible for a node to have more than one incoming edge. So if each node only has one outgoing edge and one incoming edge, then it's going to form a cycle. Of course, there are exceptions. Like for example, instead of a cycle, it might just be a lone node. So in this sample right here, 5 doesn't have any swaps connected to it. So it's just one lone node represented by 5 and then times 0. Okay, so what this means is that if we really just have a bunch of different cycles in the graph, then what we can do is we just process each cycle and count the number of distinct nodes in each cycle. And then at the end, we can simply iterate through all the cows and just their answer is equal to the size of the cycle they're a part of. So we reduce the complexity by a factor of n. It's just O of n times k now. Now, how do we speed this up even further? Well, as you might have noticed, the timestamps that you can reach a position at can only be the times written on the swaps that it is adjacent to. It can only be the times that are written on the edges. And so for a given position, so for a position, there are really only number of edges. There are only this many times at which we can reach it. And so if we only keep track of the times that we can possibly reach it at, then the sum of all the times across all the nodes is going to be k, because, or rather 2k, because each edge only contributes a time to the two nodes, the two positions that it is connected with. So there are only a total of O of k, O of, yes, there are only a total of O of n plus k nodes. And so the complexity is reduced to O of n plus k, because there are only O of n plus k nodes, and each node is part of some cycle, and we can process all the cycles also in linear time. So let's recap the solution, because a lot just happened. So in essence, a recap of the solution is that we characterize this whole relationship based on the time at which you visit a position. So we say that if you reach a position at a certain time, then you know exactly which edge you're going to take next out of the different edge options that it has. And so if we build a new graph with a node characterized by its position and a time, then this new graph is going to be a set of cycles. And now we just simply need to run through all of these cycles, count the number of distinct nodes in each cycle, and attribute that to each of the cows depending on which cycle they are in. And since there are only O of n plus k nodes, each with exactly one outgoing edge and one incoming edge, the complexity is O of n plus k. Yeah, so this is a bit complicated, so maybe writing the code will help elucidate some questions you might still have. Let's go write some code. So I'm going to begin by taking in the input. So we have n and k, and we have a series of k swaps. And I'm going to use zero-based indexing because I like zero-based indexing. And so I'm going to store the swaps in an adjacency list. So I'm going to go ahead and I'm going to create a adjacency list. This adjacency list, these edges are going to also store their time on them. So so let me just go ahead and do that. Here we go. So that's our adjacency list. Awesome. So now what is the first step? The first step is to actually build our graph. So what we can do is we can do it like this. So for every so our node is going to be, let's do this. So this is I'm going to name this adjacency initial to represent our initial graph, because later we're going to build a difference graph based on our node time pairs. Yes, so now I'm going to create a new graph called adjacency node time. And this is actually going to be, I'm going to make this a map. And the reason why I'm making this a map of then vectors is because you have to remember that our node time pairs described by both the position. Actually, I'm mixing up the words node and positions. This is position time pairs. So the pairs are described by the position and the time at which time of arrival. And so the way I'm going to index them is I'm going to do like adjacency of position time. I'm going to grab the position, and then I'm going to grab from the time the actual time, and I can then access this given adjacency list. And I use a map because the times are from 1 through n, but I can't actually declare like a 2D array because that would be too much memory. So let's do this. I'm going to iterate over every single position. And then I'm going to iterate over the adjacency list. And then, so we're currently at, and so basically when we arrive at this given time, we're going to exit through the next time. So let's do this. So we have adjacency init of ij is going to be that given, is going to be the current pair we consider. How about that? Yes. So say we just came in, because remember these edges are characterized, the edges are characterized based on, so I guess this is the other position it's connected to and the time that this swap occurs at. So I'm going to go ahead and say the current time that I just arrived at is going to be this. So this is the time I just arrived at, and it just came from this other position. Now the next one is going to go to is going to just be the very next edge, because you notice here that these edges are already sorted based on time, because that's the order that we inserted them into the list. So I'm going to go ahead and say adjacency init, adjacency position time, sorry. So currently at this position, currently at this time, we have an edge to the very next one, which is going to be adjacency init I, the very next edge. I'm going to take this mod the adjacency init size, because I'm taking a mod the size because well, if we're at the, because if you're at the final time, then you wrap around back to the first time again, if you remember that. And so yeah, it's just that pair actually. Yes. This is a little bit complicated what just happened here, but if you just, I guess if you just like want to stop and think, pause the video here and just think about what exactly this is doing. This is essentially saying that when I arrive at this time, the very next edge in the adjacency list is going to be the next edge that I take. So I'm going to go ahead and draw an edge from this position at this current time to the next position and the next edge this time. All right, so now we've built the graph. We need to now kind of walk through this graph. So let's go ahead and do this. So I'm gonna go ahead and create was assign to each pair a cycle ID. So essentially each node is going to be part of some cycle. And so nodes with the same cycle ID will have the same answer. So now here's what I'm going to do. So initially the ID is going to be, the ID of the first component will be 0. So what to do is I'm going to iterate for every single cow. So remember, this is actually, so when we actually calculate the final answer, we want to start from the position I and time equal to 0. Now time equals 0 does not necessarily exist, right? So instead, what we're going to do is it's equivalent to the same thing as starting from time I and the last time in I's last time in I's adjacency list. This will give us the same effect as starting from a dummy node called time of I 0. And if you want to think about why that's the case, just think about how like the very next edge that's I and the last time it's going to take is going to just be the first edge in the adjacency list, which is what we want. Because it wraps around. Okay, so we have cycle ID. So essentially, if this component. Actually, let's do a different case. So it's possible that the adjacency list is just empty, which means we just have the answer is just 1. So if adjacency of I is empty, adjacency init, then I'm just going to print 1. Otherwise, if this node has not already been computed as part of some cycle, so it doesn't have a cycle ID. What's the time again? The time is going to be the last time. So if it doesn't already have a cycle ID, then we're going to go ahead and explore the cycle containing IT. Let's just go ahead and explore the cycle right now. So how are we going to explore the cycle? We just need to walk around and we need to accumulate all of the values. So I'm going to go ahead and also store an answer array. I'll make this size 300,000. Yeah. So I'm going to go ahead and store. So I'm going to go ahead and say the cycle ID of this is going to equal ID. Yes. And now I'm going to keep walking around the cycle. So here's how I'm going to do it. Actually, I just realized that adjacency position time doesn't need to be a vector because there's only one outgoing edge. So we can simplify this to just a pair. So that was my bad. But yeah, so it's just a pair now. Okay, cool. Yeah, because there's only one outgoing edge, so it's not really an adjacency list. But anyways, from this position, we're going to walk. We're going to walk along the cycle. So while, actually, let's do it this way. Okay, so I don't want to change the value of I because I is being used in this for loop. So I'm going to make a new variable called U. And now while does not contain that, we're just going to go ahead and we also want to collect all the unique values. So we're going to have a set that's going to collect all the unique values, the unique positions that we encounter. We use a set because we don't want to accidentally count like, for example, position 3 times 4 and position 3 times 6 as like 2 different positions. They're both the same position, just at different times that we arrive at them. So we're just going to walk. So while we have not, so in this case, I'm essentially using cycle ID also as a visited array. So if a cycle ID has already been set for this node, that's equivalent to saying it's visited. So this is like an equivalent, this is like basically equivalent to me using it as a visited array in like a DFS or something. Go ahead and insert this node, and then we'll just go ahead and move to the next one. So we want adjacency position time. Just go ahead and also set this. Go ahead and set this ID now. Auto next is equal to adjacency position UT. So this is actually a pair. I'll specify that. So we're gonna go to the next node, and then we'll just set this stuff. All right. And then when we're done with that, the answer for this given component is just equal to the size of the set. And finally, we're going to increase the ID because now the next component will be a different ID. We're just going to go ahead and print the answer for this component. Yes, okay. All right, that was very complicated, but hopefully this works. Four, 4, 3, 4, 1. That is correct. Let's take a look and see how many points we can get. Oh, okay. Oh man, that was a long one. Alrighty, so this should be fine. Let's wait for the last few test cases. Come on now. And perfect. Okay. And all right, so that's the solution. I think I may include, yes. So just to recap what I've done here, essentially I have my, so essentially what we've done here. So at the end of the day, what we did was we built a separate graph based on position, time of arrival. We walked around all the cycles and we found all the unique nodes. So I think I will post this code maybe in the description somewhere or something. And if you want to check this out and just scrutinize over this code yourself, then you can feel free to do so. This is definitely a pretty tricky problem to implement for a silver, in my opinion. So that's it for this video. Thank you for watching.